Hey, and welcome to this lesson about ratios, proportions, and similarity. In this lesson, our essential question, what can we recall about ratios and proportions? So we're going to review what a ratio is and review what a proportion is. We're going to use those properties to talk about congruency and then get into similarity and similar figures. So starting off, we can define a ratio as a comparison of like objects. For example, a common ratio might be uh, 1 over 2. It's written as a fraction, saying 1 to 2 is the ratio. Also written 1 colon 2. And also just written verbally 1 to. I have a 1 to 2 chance of getting a heads when I flip a coin. For example, every time I flip a coin, theoretically, every 2 times I flip it, one of those times will be a heads. So where else can we use ratios? Let's think about if you played baseball on a local club team and last year you hit the ball 52 times. Is that good? Well, it kind of depends on how many times you went up to bat. If you went up 60 times and got 52 hits, then that's really, really good. If you went up to bat 1,000 times and only got 52 hits, that's really, really bad. So the greater the ratio, so think about it's a fraction, so the higher the numerator, the better the ratio. So let's see here. You play baseball on a local club team. Last year you hit the ball 52 times. You were at bat 108 times. Now we can compare. So let's do the number. Let's compare the number of hits to the number of at-bats. So our ratio is the number of hits to the number of at-bats. So our number of hits is 52 to the number of at-bats 108. Now it's important to remember to always put your ratio in the simplest form. So if we have the ratio of 52 at-bats to 52 hits to 108 at-bats, we want to simplify that a little bit. 52 we can divide by 4 and get 13. And if we divide 108 by 4, we get 27. So our simplified ratio would be 13 to 27. So every 27 at-bats, I should get 13 hits if I'm keeping the same ratio of hits to at-bats. So there are 13 girls and 15 boys in the class. So what is the ratio of girls to boys? Well, if I'm doing girls to boys, so girls to boys, or girls to boys, then I'm going to just replace the number of girls with the number of girls and then put the number of boys to where I wrote number of boys. So the number of girls is 13 to the number of boys, which is 15. Down here similarly as 13 to 15 using a colon. So there are 15 girls and 15 boys in a class. The ratio of girls to boys is 13 to 15. There are 6 red balloons and 3 blue balloons for your party. What is the ratio of blue to red balloons? So we have 3 balloons, 6 red balloons. So the number of the ratio of blue balloons to red balloons can be written as 3 to 6. However, that can be simplified. And it's kind of easier if you look at it as a fraction, but you can do it both ways. 3 to 6, they both can be divided by 3, so we can reduce that ratio to 1 to 2. Same with the fractional form. 3 to 6 can be reduced to 1 to 2. Now, proportion is an equation of two ratios. So, if I have, for example, my ratio is 1 to 2, I may have a ratio that's 4 to 8. Those ratios are equal, and so I have an equation, 1 to 2 equals 4 to 8. They are proportional ratios. They are in proportion with each other. Those two ratios are equal. Therefore, they are in proportion. So proportion is an equation or an equality of two ratios. So when two ratios are equal to each other, they are in proportion. In the last example, for the ratios, we found that the number of blue balloons was 3 to 6, and then we also reduced that to 1 to 2. Well, if I put both of those in fractional form, since I simply reduced here, I didn't change the proportion of balloons I didn't change the ratio at all. It's still the same ratio. I didn't change the ratio of balloons or blue balloons to red balloons. I simply rewrote the proportion or rewrote the ratio in a simplified way, or a smaller proportion. So I can write this as 3 to 6 is equal to 1 to 2. Now, how can we prove that? We're going to use what's called the cross multiply property. We're going to cross multiply. We're going to multiply each side by 2. So I'm multiplying this side by 2. That's what it's going to look like, because the 2's will divide to 1 over here. So really, I'm going to multiply by 2 over here. And then I'm going to multiply both sides by 6. And so what will happen on the left side now is that the 6's will divide to 1. And essentially, I'm only multiplying the right side by 6. Excuse me. And I'm getting rid of the 6 in the denominator on the left. So what it will look like is 2 times 3 equals 6 times 1. And if I multiply out the left side, I get 6. If I multiply out the right side, 6 times 1, I get 6. And that, we can see, is a true equation. Therefore, the ratio 3 to 6 is equal to the ratio 1 to 2, and therefore they are the same. They're in proportion to each other. Now, we might have to find x, or just an unknown variable when solving, when talking about proportions and ratios. So, for example, it's common in recipes. If I wanted to double a recipe, or if I had a recipe that called for 5 cups of sugar and it made 8 total cups of cookies, let's say, and I wanted to make, well, I needed 56 cups of cookies. How much sugar should I put in? Remember, when cooking, the ratio of your ingredients is very important. You have to maintain the same ratio. So, in order to keep it proportional, if I increase my total cups to 56, from 8 to 56, how many cups of sugar would I need? So I'm going to put x there. And what I'm going to do is I'm going to cross multiply. I'm going to times 56 by 5, and then 8 times x. Now, you could think, well, why did we even multiply 8 here? Well, once you get better at these, you won't have to do that step. You'll see that, okay, all I need to do is multiply the left side by 56 and the right side by 56, and I know that the 56's will divide to 1. So, essentially, I'm going to have 56 times 5 divided by 8 equals my x. 56 divided by 8, and we get 7. And so 7 times 5 is going to be 35. So x equals 35. So if I'm making 56 total cups of cookie dough, I would need 35 cups of sugar in order to keep the ratio the same, and therefore have a proportional recipe. Let's try this example now. Let's multiply by 2. And you get 42 times 3 over 7 equals x. These 42 divided by 42 divides to 1. And so 42 divided by 7, we can simplify that into 6 over 1. So 6 essentially times 3 equals x. 6 times 3 is 18, so 18 equals x. Now, this one's a little trickier. We do need to multiply both sides by the denominators. So we do need to cross multiply here. We need to do this for both sides because x needs to be in the numerator. So therefore, we do 6 times 5 equals 30 times x. 6 times 5 equals 30. And so I have 30 equals 30x. If I divide both sides by 30 to isolate the x, 30 divided by 30 on both sides is 1, so 1 equals x. Now, we said when two ratios are equal, they're said to be in proportion. Now, if two objects have the same ratio of, let's say, sides, two corresponding parts have the same ratio, then those two objects that have the same shape, so they have the same basic shape. So let's think about triangles, for example. The triangle had the same exact shape, but one was just bigger, so the sides are in proportion to each other, then those are considered to be similar. So two objects that have the same shape, whose sides are in proportion, or any objects, or any part of the figure or object are in proportion. So where do we see this? We see it in model cars. If you look at the bottom of some model cars or just drawings of cars, you might see a little, what we call a scale. So here, the ratio of the model to the real size of the car is 1 to 18. So the actual car is 18 times bigger than the model drawn. And so it says approximately 10 inches long here. So we could set up a proportion that says if the model of the car is approximately 10 inches long, well, how long is the actual car? So if I have the ratio of 1 to 18, and that's the ratio of the size of the model to the size of the actual car is 1 to 18, I can set a proportion and say, well, I know the length of the model car. Let's find the length of the actual car. They're going to be the same ratio because they're in proportion. They're similar figures. That's what this scale means. So if we solve this proportion, we would get x equals 180. Now remember, that's inches. It says it's 10 inches long. So if we do 180 divided by 12 to convert to feet, we would see that the car is 15 feet long. It is 18 times longer than the scale model. That 18 is your, what we call a scale factor. Over here on the right, an architectural drawing of a floor plan. The scale, or the scale factor, well, the scale is is the ratio of the drawing to the real life building. So 1 to 200 means for every 1 inch is 200 inches, or every 1 foot is 200 feet in the real life drawing. So the scale factor for the drawing would be 200. So here's one last example of a scale factor. So 1 inch equals 2 feet. So for every 1 inch, it really accounts for 2 feet in the real sized room. So let's figure out how wide this fireplace is. So from here to here, it says, I don't know if you can read that, but it says 2.5 inches. So 2.5 inches is how many feet in real life? So let's set up a proportion. Well, 1 is to 2.5. Those are the inches. As 2 feet is to X feet, right? I want to know how many feet the fireplace is wide. And in case you didn't know, this double apostrophe means inches. It's a shorthand for inches, and the single apostrophe is shorthand for feet. So if I do, if I cross multiply here, I get X equals 2.5 times 2 is 5. Since X is in feet here, that means that the fireplace is 5 feet wide. And that's all for this lesson. I hope you learned a lot. Hope you really reviewed and were able to dust off the cobwebs and some things that helped you remember what ratios were and what proportions are. And I hope you got a good introduction to similarity and how we can use it in geometric figures.